In this video, we'll provide some intuition for attention and contrast some different types of attention. Let's dive right in. Intuition for attention. Throughout this lecture, we will mostly look at explicit ways of getting our neural networks to attend to certain parts of the input. But before we get to that, I would like to mention that already standard neural networks, such as convolutional neural networks, actually implement an implicit type of attention already. By that I mean that trained neural networks actually already react more strongly to some parts of the input than to others. We can quantify this, for example, by taking the gradient of a class probability output, so the probability of us outputting a certain label for an image, with respect to the input pixels. So we simply backprop not only to get the gradient of the weights with respect to the class probability, but we backprop further all the way to the input pixels. And then we can, for example, look at the gradient of the probability of outputting the label dog with respect to an input pixel I, and that would tell us if we wiggle this pixel I, how does the probability change that the output is going to be dog. And this allows us to actually compute a so-called saliency map with a single step of backpropagation for an image like this, where there's a dog here, and there's also high values of this gradient of this class probability with respect to these input pixels, but not with respect to all those input pixels here. And that tells us, well, that these highlighted input pixels are particularly important for determining whether the output is going to be dog. And well, it's kind of nice that we can do this with a single backprop, but it's important to notice here that this is an implicit attention mechanism. This information is not actually used in the neural network as part of the computational graph or anything. The network actually never looks at these highlighted pixels more than at other pixels. It just so happens that these pixels matter more for computing its output probability of the label dog. But actually in explicit attention, the network explicitly focuses on some parts of the image. We see this in this example where we're trying to classify this bird here. Well, actually this bird is more like this. And this area here is also much highlighted. And this explicit attention mechanism here actually is part of the neural architecture. The rest of the neural network does not actually act on this original input data, but it acts on this weighted input data. So the network actively takes into account that not all parts of the image are equally important, and it weights these important parts of the image here more highly and actually changes the input representation to this weighted input representation and downweights the other inputs. Now, this can be seen as input-dependent weights. And well, this is called weights because, well, you multiply the inputs with these weights, you weigh the inputs, but these weights are not to be confused with the trainable parameters of the network, which we also often call weights, but they are the output of a computation, namely the output of the attention mechanism. And this attention mechanism, well, that has trainable weights itself, and that computes these attention weights, and it is learned jointly together with a classifier that actually then uses this weighted input representation. Now, These explicit attention mechanisms are actually not so new to you. We've actually already seen this, for example, in the input gate in LSTMs. Well, that input gate depends on the input, and it determines how much the input actually affects the LSTM state. And very specifically, it actually multiplies the input by, well, how much the input gate is open. So this is very much a input-dependent attention weight that is computed by an attention mechanism, namely the LSTM's attention mechanism. And well, these attention weights are also not the trainable parameters, but they're the output of this attention computation. These explicit attention mechanisms can have various benefits over implicit attention. They can lead to greater computational efficiency if you have some of the weights actually go to 0 and you get sparse attention or hard attention. They can also lead to much greater scalability because it allows you to look at much higher resolutions of images and much higher input dimensions because you only focus on some parts of the image that are important, or in general of the input that are important. And it also allows you a certain amount of interpretability by looking at what parts of the input the network actually focuses on. And because of that, in this lecture and in all of deep learning these days, we focus on such explicit attention mechanisms. Now we've seen implicit versus explicit attention. There's also hard attention versus soft attention. And hard attention actually has binary decisions for should you pay attention to this input or should you not pay attention to it. The advantage of that can be computational savings, but the disadvantage is that, well, this is hard to train because it's not differentiable. And soft attention, that actually has continuous weights for all the different inputs. The advantage here is that it's directly trainable via gradient descent, just like in the LSTM. But the disadvantage is that, well, this can actually be computationally costly. However, there's lots of research for actually trying to make this cheaper. And this soft attention is indeed the type of attention that we'll discuss throughout the lecture, and that is the by far most widely used type of attention throughout deep learning. Hard attention has been used in the past, but it's more important for historical reasons. And this brings us to the end of this lecture. And as always, I'd like to leave you with some questions for you to activate the material. I'll see you in the next video. Thank you.